Hi everyone, welcome back. This second video really looks at other examples of topographical maps, and the main point is to say that some of the properties that we've seen in the case of vision that's been particularly well studied in the brain also apply to other sensory modalities and indeed to action. So that's what we're going to be looking at in this video. First of all, we'll think about sound and the way that different auditory frequencies are mapped onto the surface of auditory cortex. So going back to the visual example, you'll remember that in order to map out the cortex with fMRI, it was possible to show an expanding ring or a rotating wedge. An analogous thing to do for sound frequencies will be to play a gradually changing sound to the participants as they lie in the fMRI scanner and see how the brain activity progresses across the surface of auditory cortex. So that was what was done in this example of a study from 2011, one of the most detailed investigations of tonotopy using fMRI. So the participants heard gradually increasing frequencies starting from about 80 Hertz all the way up to something like 8,000 Hertz and increasing over the course of 32 seconds in short bursts. So something like burp, 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 something like that, you can imagine. And as they were hearing that sound, waves of activation passed across their auditory cortex. And in D here, you can see a close-up of the map that was observed in an individual participant. So for this participant, the lowest frequencies activated a region right in the middle of Heschl's gyrus, which is where primary auditory cortex is. And then as the pitch increased, the wave moved away from that middle region progressively towards these higher regions on either side. So there's a sort of mirror symmetry to that map. Starts with the low frequencies in the middle and then represents the higher frequencies moving further away in each direction. And that pattern was seen not just in each individual, but in the group average across 10 different people. So it seems to be a pretty reliable feature of the tonotopic map in humans. This study was carried out about 10 years ago, and it's one of the more detailed studies of tonotopy. So we've already seen a couple of examples of topographical maps in the brain, where some parameter, some feature of the external world is mapped on to the surface of the cortex. We've seen retinotopy, where the visual field is mapped onto the visual cortex. We've seen tonotopy, where the range of different frequencies that we can hear is mapped onto the auditory cortex. And we can also think about somatotopy. That's when the body's shape and surface is mapped onto the surface of the brain. And that can happen in at least two situations: somatosensation, which is concerned with the sense of touch as it originates from different parts of our body, but also with motor control, where we can generally move those same parts of the body. Some of what we know about somatotopy originates from investigations carried out by neurosurgeons. And just as a warning to anyone who might be sensitive to it, on the next slide I've just got a photograph, black and white photograph of some brain surgery. It's not particularly shocking, but if you are concerned about it, you might want to just look away for a couple of seconds. It won't be on the screen for very long. So these were investigations carried out by neurosurgeon Wilder Penfield and his colleagues, and they advanced the understanding of topographical organisation in the brain by stimulating specific locations in patients' brains while they were awake during brain operations. You might be surprised to learn that patients are sometimes awake during brain surgery, but it remains a common procedure to this day because surgeons need to be able to pinpoint those areas that are controlling critical functions such as speech to ensure that they don't get damaged during the operation. And so it's a safety procedure, and it's one that Penfield and his colleagues sort of pioneered, but in a more exploratory approach. They tried to probe all of the different parts of the brain to understand what was going on, which parts of the brain controlled or responded to which parts of the body. And so in this way they were able to build up maps like this one. So this is the map for somatosensory cortex, which lies just behind the central sulcus in the brain and represents touch and other bodily sensations on different locations of the body. And what you can see is that the different parts of the body are laid out very systematically over the surface, so that nearby parts of the body are represented near to one another on the surface of the cortex. there's a systematicity, there's a topographical organisation to the way that the body is laid out on the brain surface. And some of those body parts are accorded a bit more space than others. So for example, the lips that are very sensitive to touch are given a bit more space. The shoulders and knees that are less sensitive to touch are given less space in the brain's representation. The left-hand side of the body is represented in the right hemisphere and vice versa. And the map is kind of upside down, so that the top of our body, the head, is represented near the bottom of the cortical map. So right on the side, the lateral surface of the somatosensory cortex. And whereas the lower parts of our body, our knees, our legs, our feet, are represented near to the top of the brain and down into the midline. So those are the parts of the body that respond to touch or local sensations in our body. And when they were stimulated during an operation, the patient might say, oh, I feel a tingling in my elbow or something like that. And the same thing can be done with motor cortex. So when these parts are stimulated, the patient might either move part of their body or feel that they're about to move part of their body. So the motor cortical map is right next to the somatosensory map. It's just in front of the central sulcus. And that is primary motor cortex. And in primary motor cortex, we see this layout of the different parts of the body kind of coarsely aligned with the somatosensory map. So the bottom parts of the body are represented near the top of the brain and in the midline, and then the head is represented on the lateral surface of the brain. But you can see that different parts of the body again are being accorded different amounts of space in the motor map. This time the parts of the body that are given the most space are the ones that are subject to fine motor control, that we can move more precisely. So another example of a topographical map, two topographical maps in fact, and again we can see that an external feature of the world is laid out systematically onto the surface of the brain. But more than that, we can see that both within and between maps, nearby parts of the brain do similar things. So for example, within motor cortex, the parts of the brain that control the movement of the different fingers are adjacent to one another in the brain. But also between motor cortex and somatosensory cortex there's an alignment, so that the head in the motor representation is roughly adjacent to the head in the somatosensory representation. Up till now we've been talking about primary cortices, so parts of the cortex that first receive sensory information from the external world, or parts of the cortex that last send out the signals to the effector organs that move our body. And you might think that these are special cases because their topographical organisation might reflect the structure of the sense organs and the motor systems that they're connected to. But in fact we see maps well beyond primary sensory cortices over and over again in the brain. So to take the example of retinotopic maps, we can see multiple retinotopic maps throughout the visual cortex, not just in primary visual cortex, and that's what's illustrated on this slide. So in this figure on the left hand side we're looking down at the back of the brain, and we can see a large number of different regions that show responses, systematic responses to those kind of retinotopic mapping stimuli that I showed you earlier on, the expanding rings, the rotating wedges. So each of these regions, V1, V2, V3, V3A, V3B, LO1, LO2, V5, and these regions within the intraparietal sulcus, IPS 0, 1, 2, 3 and 4, each of those regions shows a systematic ordered response to those retinotopic mapping stimuli, representing either all or part of the visual field. And on the right hand side we see a similar pattern on the ventral surface of the brain. So here we're looking up at the underside of the back of the brain, and again we can see multiple field maps in these different visual areas. So we know these visual field maps, these retinotopic maps, are not restricted to areas of the brain that are solely concerned with low-level visual processing. Instead, they extend to areas of the brain that are involved in much higher level computations. So for example, IPS is involved in computing actions in the immediate environment. So for example, reaching out and touching an object. And on the ventral surface of the brain, area V4 might be involved in shape coding, and more anterior regions might be involved in selectively processing different types of object. But here again we see visual field biases, so the part of the brain that responds most strongly to faces is also more responsive to the central part of the visual field, while the parts of the brain that respond more strongly to places are more responsive to the peripheral parts of the visual field. It seems to me and this is more my personal opinion than an established fact, that wherever we look, we will eventually find maps. The further we get away from the primary cortices, the harder they are to find, and that's because we don't always know what the neurons are encoding. Neurons are no longer responding to simple sensory and motor variables, and so it's hard to create these stimuli that systematically probe the map. So we don't know what the key variables are, but wherever we have been able to establish the key variables, we've seen signs of topographic organisation. So here's a final example from the hippocampal formation, a part of the brain that's about as far away from sensory and motor systems as it's possible to get. And yet even within this structure, it's possible to see signs of topographical organisation because we know something about what those neurons encode. So you'll see on the top row, and you'll be familiar with the idea of place cells. These are cells that encode the location of an animal within its environment. On the bottom row, you can see grid cells. Grid cells are like place cells but show multiple fields within the same environment, and those fields are organised in a triangular grid, so they're very regularly spaced. Both place cells and grid cells have a kind of spatial scale, represented by the size of the place field or the spacing of the grid fields. Intriguingly, it looks as if this abstract property, spatial scale, might be the thing that's topographically organised in the hippocampal formation, because at one end of the hippocampal formation we find place cells that have very small firing fields, and we find grid cells whose firing fields are very closely packed. And at the other end of the hippocampal formation we find very large place fields and very widely spaced grid fields. So it looks as if spatial scale, which is something that's evidently encoded by these neurons, is also organised in a topographical way systematically along the length of this structure. So I've given you several examples of topographical maps from across the brain, and although I don't think it's an established fact, I'll nail my colours to the mast. I think it will turn out to be a general principle for how the brain's organised. I don't think it's all random, and I think that if there are general principles, we should try to understand them as well as we can, so that we can try to understand how the brain comes to be like this. And so in the next few videos I'll be looking at some general properties of topographical maps in the brain, and also exploring how they come to be the way they are.